In 1963, a respected astronomer announced he had found a giant planet orbiting Barnard's star, a dim red dwarf just 6 light-years away. For over a decade, textbooks treated it as fact. Then the planet vanished. A quiet adjustment to the telescope lens had introduced a phantom wobble, mimicking a world that never existed. Decades later, a promising super-Earth signal around the same star dissolved into a mathematical alias of its own slow rotation. Yet after a century of false starts, real planets have now been confirmed there. Small, compact, and nothing like anyone predicted. Whether anything could live on worlds orbiting this ancient star is a story that begins on a set of glass photographic plates from 1888. Edward Emerson Barnard spent long nights at Yerkes Observatory in the late 19th century, his attention fixed on a faint, reddish point among thousands of stars. Between 1888 and 1890, he and his colleagues exposed glass photographic plates using the 40-inch refractor, each plate capturing a tiny patch of sky with remarkable clarity for the era. These glass plates, about the size of a large notebook, held the faint image of what would become Barnard's star. Barnard's method was patient and exacting. He examined each plate under a microscope fitted with a measuring eyepiece, a micrometer, allowing him to pinpoint the star's position to a fraction of a millimeter. To ensure accuracy, he compared the star's placement against a grid of reference stars, whose coordinates were already cataloged. Every measurement was carefully recorded in his handwritten notebooks, alongside notes about the telescope's settings, the plate scale, and the night's seeing conditions. The real breakthrough came when Barnard compared the earliest Yerkes plates from 1888 and 1890 with a follow-up exposure taken in 1904 using the Bruce telescope in South Africa. The two images, separated by 16 years, revealed an unmistakable shift. Where most stars clung to their positions, this one had drifted northward by more than 160 arcseconds, enough to be measured directly, even with the modest tools of the day. Barnard calculated a proper motion of 10.3 arcseconds per year, a number so large that it startled the astronomical community. For context, that's about the width of the full moon sliding across the sky in just 180 years, a pace unmatched by any other star then known. Barnard's own words, published in 1916, described the star as racing through the heavens at a rate that seems almost incredible. He went further, estimating the star's distance using the parallax method. By measuring the apparent shift in position of the star as Earth orbited the Sun, Barnard arrived at a value of about 1.83 parsecs, just under 6 light-years away. Modern measurements from the Gaia satellite have refined this to 1.828 parsecs, a difference of less than 0.1% from Barnard's original calculation. The agreement is a testament to the rigor of his approach and the power of simple geometric reasoning. The Yerkes plates themselves, now preserved in the University of Chicago's archives, still show the faint trail of Barnard's star inching across their glassy surfaces. Each plate, each micrometer reading, and each careful correction for atmospheric distortion and precession laid the groundwork for the precise astrometry that would follow a century later. The discovery of Barnard's star's extraordinary motion began not with computers or satellites, but with a quiet observer, a set of glass plates, and the patient accumulation of evidence, night after night. A century after Barnard's careful measurements, the search for accuracy has moved from glass plates to the cold, silent orbits of satellites. The Gaia mission, launched by the European Space Agency in 2013, now serves as the gold standard for measuring the positions and distances of stars throughout the Milky Way. Gaia's detectors track the subtle dance of stars with micro-arcsecond precision, an angular measurement so fine that it can distinguish the width of a human hair from 1,000 kilometers away. For Barnard's star, Gaia's early data release 3 provides a parallax of 546.976 milliarseconds, corresponding to a distance of 1.828 parsecs. The uncertainty in this measurement is just 0.040 milliseconds, a margin so slim it would take more than 25,000 years for the star's motion to shift by even that amount. The mission's catalog also records the star's proper motion, minus 0.603 arcseconds per year in right ascension, and plus 10.503 arcseconds per year in declination. Combined, this yields a total sky drift of about 11.02 arcseconds per year, slightly higher than Barnard's own estimate, thanks to Gaia's ability to account for motion in both directions and its use of a stable, space-based reference frame. With these numbers, Gaia has not only confirmed Barnard's century-old calculation, but also refined it to the point where even the smallest deviations can be detected. Gaia's precision extends beyond measuring distance and motion. Its data allow astronomers to search for the telltale wobble that a massive companion would induce in Barnard's star's path. If a Jupiter-sized planet orbited at a distance similar to Earth's from the Sun, Gaia would see the star trace a tiny ellipse on the sky with an amplitude of a fraction of a millisecond. Instead, the catalog reveals no such wobble above 0.1 milliseconds, a limit that rules out any hidden giant planets within a few astronomical units. Barnard's star appears alone, with no unseen companions large enough to escape Gaia's notice. This level of certainty has practical consequences. For future missions aiming to visit or observe Barnard's star up close, the Gaia solution provides a roadmap accurate enough for interstellar navigation. The error bars are so narrow that a probe launched today would arrive within a few million kilometers of its target, even after traveling for decades at a significant fraction of the speed of light. As a result, the star's distance and trajectory are now locked down with a confidence that would have astonished Barnard and his contemporaries. Gaia's catalog stands as both a validation of early 20th century ingenuity and a foundation for 21st century exploration. Barnard's star is a member of the M45 class, a type of red dwarf known for its low mass and faint light. Its mass is about 0.16 times that of the Sun, just a fraction of what we are used to in our own stellar neighborhood. The radius is even smaller, measuring only 0.185 solar radii. This means Barnard's star is less than 1/5 the size of the Sun, and if placed side by side it would look like a glowing ember compared to our familiar yellow disk. The surface temperature, or effective temperature, is around 3,200 Kelvin. That is cooler than the Sun by more than 2,500 degrees, giving Barnard's star its characteristic deep red hue. Its faintness is even more striking when considering total energy output. The luminosity is just 0.00356 times that of the Sun. In other words, Barnard's star emits less than 0.4% of the Sun's energy. If Earth orbited this star at its current distance from the Sun, our planet would be plunged into darkness and deep freeze within days. These measurements are not guesses. The radius comes from interferometric observations. Astronomers use arrays like the Chera interferometer to resolve the tiny disk of the star and measure its angular size directly. The mass is inferred from well-tested relationships between mass and luminosity for nearby M dwarfs, cross-checked by the precise parallax and apparent brightness. To find the luminosity, astronomers apply a bolometric correction to the star's measured brightness, accounting for the fact that most of its energy is radiated in the infrared, invisible to the human eye. This combination of low mass, small radius, and meager luminosity defines the environment around Barnard's star. The habitable zone, the region where liquid water could exist on a planet's surface, lies much closer in than in our solar system. Only planets orbiting at 1/10 or even 1/20th of Earth's distance from the Sun would receive enough light to support temperate conditions. But proximity brings its own set of challenges, from tidal locking to increased exposure to stellar flares. Each of these factors shapes the prospects for life and the architecture of any planets that may circle this quiet, ancient sun. Barnard's star carries its age quietly, like a well-worn stone at the bottom of a stream. Astronomers estimate it to be around 10 billion years old. more than twice the age of our Sun. This great age is written into the star's very nature. Its slow, measured rotation is one of the clearest signs. While young red dwarfs can spin on their axes in a matter of hours or days, Barnard's star takes about 140 to 145 days to complete a single turn. This lazy spin is the result of billions of years spent shedding angular momentum, mostly through winds of charged particles that, over time, have acted like a cosmic brake. The slow rotation has profound effects deep within the star. In stars like the Sun, swirling layers of hot plasma generate powerful magnetic fields through a process known as the dynamo. But Barnard's star, with its fully convective interior and gentle rotation, produces a much weaker magnetic field. The result is a star that is magnetically quiet, with only a few hundred Gauss on its surface, far less than the turbulent fields seen in younger, more active M dwarfs. This magnetic calm is reflected in its behavior. Over decades of monitoring, only a single notable optical flare has been recorded in 1998. Most of the time, Barnard's star sits in a state of deep quiescence, emitting little in the way of X-rays or ultraviolet light. Its rare flares are modest compared to the violent outbursts seen on many other red dwarfs. For any planet close by, this means less frequent bombardment by high-energy radiation, though even rare events can have lasting effects on planetary atmospheres. The star's ancient, subdued dynamo and its slow, steady pulse offer a kind of stability. Yet this stability is a double-edged sword. The same processes that quiet the star also limit the magnetic protection available to any orbiting planets. Without frequent flares, there is less immediate danger from radiation, but the weak magnetic field means less shielding from cosmic and stellar wind particles. In the delicate balance between calm and vulnerability, Barnard's star stands as a serene but exposed beacon, a reminder that in the cosmos, longevity and tranquility come with their own quiet risks. In the early 1960s, the quiet halls of Sproul Observatory became the unlikely stage for a drama that would ripple through exoplanet science for decades. Astronomer Peter van de Kamp spent years tracking Barnard's star, convinced he had found evidence of a giant planet tugging subtly on its path. His method relied on astrometry, the painstaking measurement of the star's position against a background grid of distant suns, recorded on glass photographic plates. By 1963, Van de Kamp announced a periodic wobble in the motion of Barnard's star, suggesting a companion at least half the mass of Jupiter, orbiting every 13 years. The prospect of a planet circling one of the Sun's nearest neighbors captured imaginations well beyond the astronomy community. Headlines trumpeted the discovery, and for a time, the existence of Barnard's star B entered textbooks and popular science writing alike. Yet beneath the headlines, a deeper story was unfolding in the fine print of the observatory's maintenance logs. In 1949, the Sproul Observatory's main lens, known as the Sproul lens, underwent a critical refiguring, a process meant to correct a persistent astigmatism. The lens was removed, adjusted, and reinstalled. At first, the change seemed to improve image quality, but it also introduced a subtle, systematic shift in how the telescope formed images on its plates. For years, this artifact lay hidden, indistinguishable from a true stellar wobble, to even the most careful observer. It was not until the 1970s that other astronomers, reanalyzing the same plates and cross-checking with independent data, noticed something amiss. The supposed planetary signal appeared only in data taken after the lens refiguring. Earlier and later measurements, as well as data from other observatories, showed no such wobble. Further inspection of the Sproul logbooks revealed the timing of the lens maintenance matched precisely the onset of the apparent planetary signature. The supposed orbit was, in reality, a mirage created by a subtle optical flaw. This episode became a lesson in the vulnerability of even the most meticulous science to hidden instrumental effects. It underscored the need for skepticism, for archival reanalysis, and for independent confirmation before extraordinary claims could be accepted. Today, The Sproul lens logs and the refigured plates serve as a cautionary archive, a reminder that the search for planets is as much about understanding our instruments as it is about understanding the stars themselves. The Van de Kamp affair set a baseline of skepticism that would shape every planet search around Barnard's star for generations to come, and it remains a touchstone in the ongoing evolution of astronomical precision. Through the first decades of the 21st century, Barnard's star stood as a benchmark for the world's most sensitive planet searches, yet year after year, the radial velocity record remained stubbornly flat. Dozens of observing runs on instruments like HARPS, UVs, and Carmines produced a string of null results, no sign of the telltale Doppler wobble that would betray a planet's gravitational pull. For a time, the absence of evidence became its own kind of story, a nearby, quiet red dwarf, apparently alone. That changed in 2018 when Ignacy Ribas and an international team announced a periodic signal in the radial velocity data. Their analysis, combining nearly 2 decades of measurements from 7 different spectrographs, revealed a 233-day cycle with a minimum mass of about 3.2 Earths. The proposed planet, Barnard's star B, would have orbited just beyond the snow line, where water ice could condense. The amplitude of the signal was only about 1.2 meters per second, a gentle nudge, but one that persisted across multiple datasets. The team used advanced statistical tools, including Gaussian process modeling, to account for stellar activity and instrumental drift, aiming to ensure the signal was real and not an artifact of the star's own behavior. Yet the claim quickly drew scrutiny. The 233-day period sat uncomfortably close to an integer multiple of Barnard's star's slow rotation, about 145 days, and to the annual observing window imposed by Earth's orbit. Critics, including a group led by Lubin in 2021, re-examined the data with even more sophisticated techniques. Their analysis showed that what appeared to be a planetary signal was actually an alias, a mathematical mirage created by the interplay of the star's rotation and the seasonal gaps in the observing schedule. When the team modeled the star's activity using Gaussian processes tied to the H-alpha spectral line, the 233-day signal vanished, replaced by noise consistent with a magnetically quiet M dwarf. The supposed planet dissolved under the weight of the data. The episode became a lesson in the subtle traps of high-precision astronomy. Even with the best instruments and statistical rigor, the rhythms of a star's surface and the cadence of observation can conspire to produce convincing but illusory signals. For the Ribas team and the broader exoplanet community, the controversy underscored the need for ever higher precision, longer baselines, and independent confirmation before any planetary candidate could be considered secure. The push for clarity would soon lead to a new generation of instruments and a new chapter in the search for worlds around Barnard's star. The search for certainty around Barnard's star has always demanded more than a single signal or a promising wobble. After the confusion of aliases and the lessons of earlier decades, astronomers turned to the most stable tools in their arsenal. Instruments like Espresso at the Very Large Telescope and Maroon X at Gemini North brought the field into a new era, where the margin for error shrank below the width of a human hair. These spectrographs, equipped with laser frequency combs, could measure the star's radial velocity changes down to just a few tens of centimeters per second, a level of precision that once seemed out of reach. With this new clarity, the story shifted. Instead of a single planet or a questionable signal, the data began to reveal a pattern: 4 distinct, ultra-short period signals, each repeating with clockwork regularity. Espresso's team, working independently and relying on line-by-line radial velocity extraction, reported planets with periods of 2.34 days, 3.15 days, 4.12 days, and 6.74 days. The smallest of these worlds carried a minimum mass of 0.19 Earth masses, the largest about 0.34 Earth masses, each one a rocky body orbiting so close to the star that a year would pass in less than a week. Confirmation came not from collaboration, but from coincidence. Maroon X, operating on a different telescope and schedule, recovered the same quartet of signals using its own red-optimized detectors. Their moving average models for correlated noise, built from scratch, matched the espresso findings almost exactly. No single team could have engineered such agreement by chance. The signal stood up to every test: different instruments, different algorithms, different observing windows. For the first time, the planet candidates around Barnard's star were not just possible, they were, as far as the data could show, real. This outcome was only possible because of the relentless push for precision. Laser comb calibration, simultaneous photometric monitoring to track stellar activity, and advanced statistical modeling all played a part. The signals survived decorrelation against every known activity index, from H-alpha to photometric spot cycles. The four-planet system, compact and orderly, emerged as a quiet victory for the methodical, skeptical approach that modern exoplanet science demands. As a result, Barnard's star now joins the short list of nearby stars with confirmed planetary systems mapped down to sub-Earth masses. The architecture, a tight, rocky quartet, reflects the broader trend seen around red dwarfs, planets packed close to their faint suns, orbiting in days rather than months. This is the scientific payoff that decades of careful measurement and independent verification have delivered. With the architecture confirmed, attention now turns to what these worlds are like, and whether any could ever support life. Barnard's star offers a harsh stage for any planet hoping to sustain life. Its faint light, less than 0.5% of the sun's, shrinks the habitable zone to a slim ring, just 0.05 to 0.13 astronomical units from the star. Even Mercury, the innermost planet in our solar system, orbits farther out. Here, a year lasts only 10 to 42 days, but closeness comes at a cost. The star's gravity locks any planet in this zone into a permanent embrace, forcing it to always show the same face. At the inner edge, tidal locking happens in under 10 million years, and even at the outer edge it is complete within 1 billion years. With Barnard's star aging at 10 billion years, any planet in the habitable zone would have long ago settled into a world of endless day and night. This locked arrangement creates brutal conditions. One hemisphere scorches under constant sunlight, while the other lies frozen in perpetual darkness. Only a dense, dynamic atmosphere could move heat between the two, but holding on to such an atmosphere is a struggle. Early in its life, Barnard's star was far more active. Its X-ray and ultraviolet radiation, though modest now, was enough over billions of years to strip away light gases from any planet with less than a third of Earth's mass. For a planet at 0.08 astronomical units, the heart of the habitable zone, models show that atmospheric escape could remove an ocean's worth of water in a few 100 million years. Over the star's lifetime, only planets with deep gravity wells, or thick, replenished atmospheres, have a real shot at keeping their air. Magnetic fields, which can shield a planet's atmosphere, face their own challenge. Tidal locking slows planetary rotation, weakening the internal dynamo. Calculations suggest a sub-Earth planet here would have a magnetic field less than 1/10 as strong as Earth's, leaving it exposed to the slow erosion of stellar wind and cosmic rays. Even rare flares matter. The strongest recorded, in 1998, blasted nearby space with X-rays and ultraviolet light. While not as fierce as storms from younger red dwarfs, these outbursts still chip away at fragile atmospheres over time. Surveys show that about half of M dwarfs, like Barnard's star, host small planets in the habitable zone. Yet so far, all confirmed worlds here huddle too close, too hot, too locked, too exposed. The habitable zone remains empty in the data. Its challenge is plain, relentless gravity, fragile air, and little protection from space. Barnard's star races through the galaxy, shifting its position by just over 11 arc-seconds each year. Over a single human lifetime, this sideways drift adds up to nearly 1/4 of a degree, enough for the star to noticeably shift among the constellations within a century. For astronomers and mission planners, this means Barnard's star is never quite where it was, demanding constant recalibration and precise tracking. Its motion is not confined to the sky's plane. Spectroscopic data show Barnard's star is approaching the solar system at about minus 110 kilometers per second. At its sideways speed, roughly 140 kilometers per second, and the star's total velocity relative to the local standard of rest reaches nearly 160 kilometers per second. This rapid three-dimensional path places it on an eccentric orbit, swinging far above and below the galactic plane, a hallmark of older disk stars. Galactic models built on modern astrometry and tools like the GALPI integration package reveal the star's future course. Barnard's star will make its closest approach to the Sun around the year 11,800, passing between 3.75 and 3.8 light-years. It will come closer than it is today, but Alpha Centauri will still hold the title of nearest neighbor. The approach is symmetrical. Barnard's star has been drawing nearer for millennia and will begin to recede after its flyby, remaining a familiar presence in our stellar neighborhood for the foreseeable future. For those contemplating interstellar missions, these figures define the challenge. At just under 6 light-years away, a probe traveling at 5%, the speed of light would need about 36 years to reach Barnard's star. Doubling the speed halves the journey to 18 years. At 20% of light speed, the trip drops to 9 years. Communication remains a major hurdle. A message from Earth today would take almost 6 years to arrive. At closest approach, the delay shortens to about 3.75 years. Real-time control is impossible, so any mission must operate autonomously, relying on preset instructions and adaptive systems. The star's rapid drift brings practical complications. Over the next 5 centuries, Barnard's star will move about half a degree, roughly the width of the full moon. Long-duration probes must constantly update their pointing systems, with star tracker corrections every few years. Even minor errors in proper motion could send a spacecraft millions of kilometers off course after decades in transit. These calculations, grounded in precise astrometry and robust modeling, turn Barnard's star's motion into engineering realities. They set the limits for what is possible and what remains just out of reach for those who dream of reaching other suns. The next chapter in the search for life around Barnard's star is being written in the laboratories and control rooms of a new generation of observatories. The Extremely Large Telescope, or ELT, rising on Cerro Armazones in Chile, is designed to collect more light than any optical telescope before it. Its segmented mirror, stretching 39 meters across, will gather faint signals from planets orbiting even the dimmest red dwarfs. For Barnard's star, the ELT's high-contrast instruments, MEDUS and Mikado, will be able to separate the faint glow of a planet from the overwhelming glare of its host, especially at the tiny angular distances that define the system's habitable zone. At 10 microns, the inner working angle narrows to just 0.02 arcseconds, enough to resolve planets orbiting at 0.07 astronomical units, right at the edge of where liquid water might be possible. Meanwhile, the race for radial velocity precision is pushing the boundaries of what can be measured from Earth. New spectrographs like Express 2 and the upgraded NED are being tuned to detect velocity changes, smaller than 10 centimeters per second, about the pace of a slow walk. With laser frequency combs and ultra-stable optics, these instruments aim to reach the level where a Mars-mass planet in Barnard's habitable zone would leave a detectable trace. The goal is clear: to move beyond the current floor of 30 centimeters per second and approach the level below 10 centimeters per second, where even the smallest rocky worlds can be found. As astronomer Jone Gonzalez Hernandez notes, the ELT will allow us to directly image planets in reflected light, not just infer them from wobbles. His colleague Priya Basant adds, "With each leap in precision, we're closing the gap between what's possible and what's detectable." These advances are not just about numbers. They are about transforming a star, once known only as a fast-moving point, into a system whose planets, if they exist in the habitable zone, could be mapped and perhaps studied for signs of life. The instruments are readying themselves for the task, and the roadmap ahead is set by the promise of discovery. Speculation about Barnard's star has always hovered at the edge of what evidence allows. A few researchers have wondered if advanced civilizations might orbit this quiet red dwarf, searching for technosignatures, signals of technology like waste heat from massive energy collectors or focused radio transmissions. In the 1970s, an Ohio State SETI survey caught a brief radio anomaly near 1420 MHz, but later analysis traced it to interference from Earth, not a message from Barnard's star. The idea of a Dyson-like structure, an artificial shell built to capture the star's energy, was raised in a conference abstract. At Barnard's distance, even a partial enclosure would glow in the mid-infrared, easily spotted by telescopes. Yet missions like WISE and Spitzer have found no such excess. Any structure capturing more than about 10% of the star's light would have been obvious. Instead, the data show only the faint warmth expected from a small red sun. Radio searches have set strict limits. The Green Bank telescope and the Very Large Array have scanned for narrow-band signals across wide frequency ranges, sensitive enough to detect transmitters radiating 10 trillion watts, far beyond anything built on Earth. No persistent signals have emerged. Algorithms now account for high drift rates, targeting transmitters on fast-orbiting planets. Optical SETI campaigns have searched for laser pulses bright enough to outshine the star for a split second, but none have appeared. Each of these efforts climbs a rung on the evidence ladder, demanding ever stronger proof. So far, every rung remains empty for Barnard's star. As one SETI expert put it, "It's interesting to imagine, but until we see a signal that survives every test, it remains just that, imagination." For now, the quiet data speak the loudest. Long after our sun fades, Barnard's star will still quietly drift past, its planets locked in ancient twilight. Today, the search for life here reminds us how much remains hidden within our cosmic neighborhood, answers shaped by the quiet persistence of data, not wishful thinking. Each new observation refines what is possible. In the end, the universe's slow revelations demand patience, and they reward it. Thank you for joining us on Sleepy Star Science. Share your thoughts below.